You might have heard this before. In 1931, one Austrian mathematician has proved mathematics incomplete, and has spun mathematics in a crisis to be never resolved to this day. Well, that's wrong. It has some truth to it, but is still wrong. Just take for example what happened to Gödel after this. He did contribute greatly to axiomatic set theory, and did partake in proving the continuum hypothesis independent of ZFC, and the axiom of choice independent of the other ZF axioms. Why would Godel put so much effort into mathematics, if he already proved its futility? Firstly, what is this theorem? Well, in fact they are the incompleteness theorems, plural. There are two theorems, not just one. The first one is the best known one, which says that, for any consistent axiomatic system, F, in which Peano arithmetic can be carried out, there exists at least one sentence that cannot be proven or disproven, i.e. the system is not complete. Generally understood as, there will always be sentences that cannot be proven. But, the preconditions are more important than one might think. The lesser known, second theorem is that, for the same system, F, its own consistency cannot be proven by itself. Which can be generally understood as we cannot prove the consistency of logic. Even though these statements are kinda true, well, it's with an asterisk and some caveats. The Gödel's incompleteness theorems are, no doubt about it, some of the most misunderstood theorems in mathematics. For starters, what is a formal system? A formal system has these following properties. 1. It has to have a formal language, which is defined as a structure of two sets of finite symbols, its alphabet, so to speak, and a set of logical connectors, and a grammar, a set of rules by which we can decide whether any statement built from them is a well-formed formula. 2. It has some axioms. And 3. It has to have some rules, with which to infer or prove, from the axioms, the theorems of this formal system. After that, there are two concepts central to our theorems, namely completeness and consistency. Consistency is an extremely straightforward concept to explain. It only means that in an axiomatic system there is no sentence P such that both P and non-P can be proven. If such a case did happen, we would have an antinomy on our hands or a paradox. Completeness, on the other hand, means that for any sentence P of said system, there is either a proof for P or for non-P, from the axioms of the system. A very interesting case of this is mathematical logic, since, well, it has no axiom so to speak, the rules for thought, or more descriptions of how to infer, not proper axioms. So generally speaking, the incompleteness theorems do not apply to it, since it is trivially consistent. Now, what are Peano arithmetics? The other precondition. Generally speaking, they are a formal system, with this following axioms, which are in some way used to build up the natural numbers, induction, and to define both addition and multiplication. And any axiomatic system that can deduce them, or implores them, in some way, can carry out Peano arithmetics. Also, as a consequence of the two incompleteness theorems, these formal systems aren't complete and cannot prove their own consistency, or they are inconsistent. But there definitely are axiomatic systems that cannot carry out such arithmetic operations, such as Pressburg arithmetics and Skolem arithmetics. Pressburg arithmetic is interesting, in particular because they do define a way to do addition, but no way to do multiplication. It is a weaker system, so weak in fact that we cannot prove the incompleteness results in it, and in fact we can prove its own consistency and completeness within itself. Yes, there are such things as complete and consistent axiomatic systems, as surprising as it may seem, but this holds for axiomatic systems that cannot carry out Peano arithmetics. Also, the other, Skolem arithmetics, well, in that axiomatic system we can construct a proof for the consistency of Peano arithmetics. Yes, because this is a different axiomatic system, we can prove the consistency of another. The second Godel theorem only restricts some systems from proving their own consistency. Actually, a lot of axiomatic theories about set theory can be proven consistent in larger theories. And some really weak ones can prove their own consistency. So, now that we understand all these counterexamples to what is commonly believed about incompleteness, we can state what they actually imply. Once you form an axiomatic system sufficiently strong to do Peano arithmetics, that system would be incomplete and you will need a bigger system to prove the original one is consistent. And so on, ad infinitum. Not the bleak view of mathematics that is usually sold. It's just a better understanding of how mathematics is an endless process. And yes, that's all for today. See you in the next video.